All right, so we've been going over position versus time graphs. Now we're going to go over velocity versus time graphs and also acceleration versus time graphs. So you're going to have three different types of motion graphs: DT graphs, position versus time or distance versus time; VT graphs, which is velocity versus time; and then also acceleration versus time. Now, on a position versus time graph, or a DT graph, you know that slope is the same thing as velocity. Well, on a velocity versus time graph, the slope is something different. You have to remember that slope is equal to rise over run. So how far did it go up? How far did the line go up? Divided by how far did the line go over, which is the same thing as delta y divided by delta x. So when you look at the y-axis of a velocity versus time graph, you have velocity. So the change in y is the same thing as the change in velocity. On the x-axis, you've got time, so the change in x is the same thing as the change in time. If you look at this is the same thing as our acceleration formula. So here, acceleration is equal to the slope on a VT graph. So on a DT graph, the slope is equal to the velocity. On a VT graph, the acceleration is equal to the slope. So when you look at this graph, so this is your first example here, when you look at this graph, you can tell that the velocity is increasing. So this object is moving along and it is getting faster and faster and faster. You cannot look at this and say, well, it's moving to the right. The slope in this case does not indicate direction. On a DT graph, the slope will indicate direction, but not on a VT graph. All this VT graph is saying right now, if I'm just looking at the slope, is that the velocity is increasing with time. So we know two things about the slope here. The first thing we know is that we have a positive slope, so that means we have a positive acceleration. We also know that we have a linear line. So this is a linear line. So if we have a linear line, that means that the slope is going to be the same at every single point. So if we know that the slope is equal to the acceleration here, we know we also have a constant slope, or in this case, a constant acceleration. So I know here I have a positive acceleration, I'm speeding up, and I also know I have a constant acceleration. So that means, yes, the velocity is increasing, but the acceleration, the rate at which the velocity is increasing, stays the same. This is really important for you to understand. If the velocity is increasing at a constant rate, so if we have a constant acceleration, the velocity is increasing, or it could be decreasing, but the acceleration is constant. It stays the same throughout the movement. All right, so let's look at another example. All right, so this one, the line is going down. So from this, I can tell that I have a negative slope. Since I have a negative slope, I have a negative acceleration. All right, I also know that I have a linear line here. Since I have a linear line, the slope is the same at every single point. So that means I also have a constant acceleration. So this object is slowing down and it is accelerating or decelerating at a constant rate. So when you look at this object, we started with a very high velocity, and now we're going down, we're decreasing our velocity as we go. When we look at this does not mean that the object is moving to the left. when we're looking at the movement of the object and what direction it's going on, that depends on the x-axis. So if the line is above the x-axis in this case, it is positive velocity, which means that it is moving to the right. Once it crosses the x-axis, it is moving to the left. So once it crosses the x-axis, velocity becomes negative. And once velocity is negative, it is moving to the left. It's moving in the opposite direction. All right, so we know that we have a negative slope, so we have a negative acceleration. And we also know that it is constant. So we have a constant acceleration. So let's go ahead and translate this into a AT graph, or an acceleration versus time graph. So again, we have negative acceleration and constant acceleration. So when I put this into an AT graph, so acceleration is on the y-axis, time is on the x-axis, we know that the acceleration is constant. Okay, so we know it's constant. So if we have a constant acceleration, that should mean that the acceleration is not changing. So if it's not changing and we're looking at this graph, the y-axis should not change. So we should have a horizontal line. So if we have a constant acceleration here, because we're graphing acceleration, we should have a horizontal line. Okay, so we also know that the acceleration on the VT graph, so this is our VT graph, look like that. So we know we had a negative slope. So since we know it's negative, so we know the acceleration is negative, it's going to have to show that on this graph. Well, this is the positive acceleration and this is the negative acceleration because it's below the time axis. So our line is going to be below the time axis because it is negative. If it was positive, it would be above the time axis and it would show that on the graph. And here's our line right there. That's what it should look like. It's constant, so it's not changing, it's staying the same throughout time. And it is negative, so it's below the time axis. All right, so now we're going to go back and let's look at this VT graph again. Okay, so we want to put this into a position versus time graph. So you have to remember that in a position versus time graph, in a DT graph, slope is the same thing as velocity. So the slope on a DT graph is going to be the same as velocity. So when you look at the velocity here and you want to translate this into a DT graph, so I'm going to make the DT graph from this, I need to look at where the velocity is. That's going to tell me where my slope is. So right here, my velocity starts off very high. So since I have a high velocity, I have a steep slope in the beginning. So it's going to increase dramatically in the DT graph. As time goes on, my velocity gets lower and lower and lower, which means that my slope will start to decrease. So my slope will start to taper off. But you have to remember, if you have velocity, you're still moving. So the object is still moving. So that is going to be shown in the DT graph because remember, you're plotting the position. So let's go ahead and start doing that. So in our DT graph, here's our position, here's the time. Our VT graph looked like this. Okay, so we started off with a high velocity, which means that we're going to have a high slope. So we're going to start off with a high slope. As we go, velocity is decreasing and decreasing and decreasing. However, this is position or distance. So if you're moving, you're still changing your distance. So you're going up, and then you start to slow down, you start to slow down, you start to slow down, and eventually you'll get to a point where you have zero velocity. So it'll start to taper off. So here is what your graph almost looks like. So you start off with a high slope here, and as time increases, your velocity becomes less and less and less. So you're going to start to taper off. However, you have to remember, you still have a velocity here. So you are still changing your position. And also, this does not indicate direction. Just because we have a negative slope does not mean we are moving to the left. We know that we're actually moving to the right because we're still above the time axis on our VT graph. All right, the hardest part about this is keeping everything straight. One thing on one graph means something different for the other graph. Okay, so let's look at another example. Okay, so here we have an object that is speeding up and then is slowing down. So this is the VT graph. Okay, so now let's look at what we know about the acceleration. So for the acceleration here, we know it's positive. We also know it is constant because it's a linear line. That means the slope will be the same at every single point in this particular segment of the line. So we have a positive, constant acceleration in the beginning. And here, since the line is going down, we have a negative slope, so it's a negative acceleration. And we also know that this is also constant. Okay, so on our AT graph, we have a positive, constant acceleration in the very beginning. So this is our acceleration, this is our time. Remember, this is positive, and this is negative. So in the beginning, we had a positive acceleration that was constant. So we have a horizontal line, because remember, if we have a constant acceleration, that means on our AT graph, we should have a horizontal line. It is positive in the beginning, so it should be above the time axis. So that's part A of the graph. Then we know that it changes. It starts slowing down, and then it's still constant. So it's still going to be a horizontal line, but it's going to be below the time axis for the second part. And I know it looks really weird here because there's no connector or anything like that, but that's what the graph should look like. We have a positive acceleration, it's speeding up at a constant rate, and then it changes to a negative acceleration. And this is fine. This is exactly what the graph should look like. I know it looks a little weird. Okay, so now let's look at graphing the DT graph. So our VT graph looks like this. Okay, so it's our time axis, this is our velocity, and we're going to graph the DT graph from this. So we know from this that in the very beginning we're speeding up, okay, and also we're starting from the 0 point. So when we start to move, we're going to gradually change our position, and then we start to speed up because our velocity is increasing, it's increasing, it's increasing. Okay, so it's going to look like a curve. It's going to be curved. Okay? Then at a certain point, I start slowing down. So I'm still moving, I still have velocity, so I'm going up, I'm going up, I'm going up, and eventually I'm going to start slowing down and go to 0, because right here it shows that my velocity eventually goes to 0. So that means my position will not be changing on the DT graph. So this is what it should look like. Okay, I'm speeding up here, but I'm gradually changing my position as I go. Okay, because remember, I cannot go from 0 to 50 meters per second instantaneously. I cannot do that. I have to gradually get to that speed because I'm accelerating. So I'm going to start off here, and it's going to gradually increase. It's increasing, so it's really fast at this point, and then it starts to decrease, and I'm still moving, so I'm still changing my position. It's still going up on the y-axis, and then eventually it tapers off. Okay, so when I'm looking at DT graphs, usually you're going to see that you have curved lines. These curved lines indicate that there is acceleration. If I actually had a straight linear line, a linear line would mean that I have a constant velocity, because that would be my slope in this case. And if I have a constant velocity, I would have no acceleration. Okay. So you have to be able to keep these things straight. So think about what you're looking at. Think about the fact that you're looking at a DT graph here. Here you're looking at a VT graph. So right here, you know, velocity is increasing, it's increasing, then it starts to decrease, okay? And then, you know, on your AT graph, well, I know I have a linear line here, so that means a constant acceleration because it's a constant slope on the VT graph. And it's positive, so it's above the time axis. This one is constant as well, and it's below the time axis because the slope is negative. So that's what it looks like. All right, so let's go ahead and review a few things. Okay, so on a position versus time graph. On a position versus time graph, your slope is going to be equal to your velocity. If you have a positive slope, that means you have a positive velocity, which means you have movement to the right or up. If you have a negative slope, you have movement to the left. If you have a linear line, that means you have a constant velocity and there's no acceleration. If you have a curved line, that means your velocity is not constant. Okay? No constant velocity. So that means your velocity is either increasing or decreasing, which means you do have acceleration. There is acceleration in the object. All right, so let's look at the VT graphs now. All right, so on a VT graph, the slope is equal to the acceleration here. If I have a positive slope, that means I'm speeding up. If I have a negative slope, I'm slowing down. The slope does not indicate direction here. Okay, the slope does not indicate direction. What does indicate direction is if your line is above the time axis. So if you are above the time axis, that means you have a positive velocity. If you are below the time axis, that means you have a negative velocity. Okay, that is what indicates your direction here. So if you're above the time axis, the object is moving to the right. If you're below the time axis, the object is moving to the left. If you have a slope of 0, meaning your velocity is not changing, so this is the VT graph right here. If I have a VT graph with a slope of 0, my velocity is not changing here. That means I have no acceleration. And then if you have a straight linear line, like this, or going down, that means a constant acceleration because the slope is going to be the same at every point in a linear line. And I think I added a few bullets. You might want to go ahead and just write those down. All right, on an acceleration versus time graph, if you have a straight horizontal line, you have a constant acceleration. And if you're below the x-axis, you're slowing down. If you're above the x-axis, you're speeding up. All right, so make sure that you really review this. And we did the practice activity in class, and like I said, if you understand what you were doing in class, you should not have an issue on a test or quiz. All right, and I will see you guys in class.